Welcome back. In this lecture, we are going to look at the space filling curves. Basically, in the previous few lectures, we have been talking about the space of all continuous functions. We had talked about the dense subsets of continuous functions, the compact subsets of continuous functions. We even extended these notions for LP spaces and so on. And now, finally, we will look at what are called the space filling curves. So let's start with this question. So the question is, do we have a bijection from closed interval 0, 1 to open interval 0, 1? And the answer is yes. So this is one example of a bijection from the closed interval 0, 1 to open interval 0. So the existence of this bijection basically means that these two sets, that is a closed interval and this open interval, have the same cardinality. In fact, this is also true. You can actually have a bijection from the closed interval 0, 1 to the entire real line. Basically means that the cardinality of the entire real line is same as the cardinality of the closed interval 0, 1. Okay, if you don't know these things, please go and have a look. So try to prove these results or find examples of these maps. So we have bijections from closed interval 0, 1 to open interval 0, 1 or the open infinite interval R here. On the other hand, there is no continuous bijection from 0, 1 to 0, 1. So here we have given a bijection here already, but you cannot have a bijection which is continuous from the closed interval 0, 1 to open interval 0, 1. This is a consequence of a simple result from the metric spaces that you know that the continuous image of a compact set should be compact. So if 0, 1 is a compact set, and if you have a continuous bijection, right, continuous map, then the image of this in 0, 1 um, should be, there is a typo here between, okay, so should be compact, right, whereas 0, 1 is not compact, so which means that the image should be a proper subset of 0, 1, proper compact subset of 0, 1, which means that you cannot, that map cannot be a bijection, basically cannot be surjection and so on. So you cannot have a continuous bijection. Okay. Similarly, if you reverse this question, that can we have a continuous bijection from the open interval 0, 1 to the closed interval 0, 1? Again, the answer is no, using again a simple result of metric space. So suppose we can prove a contradiction. Suppose say there is a continuous bijection from open interval 0, 1 to closed interval 0, 1. Then you can choose two distinct points x and y in the open interval 0, 1 such that x is mapped to 0 and y is mapped to 1. Okay. Now depending on whichever x is less than y or y is less than x, you can look at the interval. So though here I have implicitly assumed that x is less than y, you could have the other way also, y less than less. So in that case you write y comma x. So basically I is the interval, I is the closed interval such that the endpoints are x and y. Okay, whichever. So ignore this thing if because this is not precise thing. This is under the assumption that x is less than y, whatever it is. So you have two distinct points x and y which are mapped to 0 and 1. These are distinct because it's a bijection, so you actually have an injective map, right? So 0 and 1 are two different points, so two different points go to 0 and 1. So you look at the interval with endpoints x and y, okay, either x comma y or y comma x, whichever is the case. So if you look at this interval, the image of this interval, this I, will be a proper connected subset of the closed interval 0 1 here, right, which will contain both 0 and 1 because x is mapped to 0, y is mapped to 1. So a connected proper subinterval of uh, 0 1 which contains both 0 and 1 is not possible because the interval connecting, I mean, having both 0 and 1, connecting 0 and 1 is actually 0 1. So this is a contradiction. So our assumption that this bijection was continuous is false. So we don't have a continuous bijection from the closed intervals to open interval and vice versa. Okay, you cannot have a continuous bijection. Now we extend this question from interval to square. So now the question that we are asking is, can we have a bijection? So similar thing like we had last year from 0 1 to 0 1. Can we have a bijection? We ask the same question. Do we have a bijection between the closed interval 0 1 to the square 0 1 cross 0 1? So this is a unit 1 square, okay, with origin as one of the vertices here, right, on the first quadrant. But that is just for simplicity. You can just take any square. Point is, do we have a bijection from 0 1 to 0 1 cross 0 1? And Cantor was the one who showed that such a bijection exists. Okay, we can actually find such a bijection from 0 1 to 0 1, and let's give a proof. Let's give the Cantor's proof of this bijection. So what he did was this: he took any element of 0 1. Now this any element of 0 1 has a decimal expansion, right? So let's say it has its point a1 because they are all less than 1, right? Greater than 0. So it's point a1, a2, so on. It's some expansion, or in another, I mean, in a much more concise mathematical form, it is an an over 10 power n, which is the decimal expansion, and these ans are numbers which can be taken between 0 and 9 because it's a decimal expansion, right? Okay, so any number from 0 to 1 has this form, has this fractional form, right? Decimal form, sorry. Okay, so what Cantor did was he defined a map from 0 1 to the square using this decimal expansion. So any element here is of this form. So the way he defined the two component as all the odd digit here were taken to be the were taken as a first component of the first element here in the square, and all the even elements here, that is even position element and odd position elements, right? So odd position elements are accumulated in the first term, and even position elements are accumulated in the second term. This is how Cantor defined this map from 0 1 to the square. But this definition and the aim is to construct a bijection. Okay, so we need to construct a bijection from C. So he defined this map. The problem with this map was this map is not well defined. That is because the decimal representation of a number is not unique, right? For instance, whenever you have a repeated nines, right, then that is approximated, and that is actually same as the nearest rounded off, because this can be seen as a series which will converge to this, right? So zero point 0.2 and 0.19999, these both these represent the same number, right? So if I look at the number zero point 0.2 in 0 1, it has two decimal representations. Now if we define the map like this, then we are going to have two different, so the same point is mapped to two different elements, and that is not even a map, or that's not even a function, right? That's not what we call a function. So it's multi-valued, right? So for instance, you can look at in this example that since point 2 is 0.11999 repeated infinite times, so if I look at what is f of point 2 and f of 0.111999, so let's see f of 0.1999 by this definition, all the odd positions, which is 1999999, and all the even positions, which is 0.9999. Okay, so the image of this element using this decimal expansion, right, point 2 using this decimal is this, which is same as point 2 comma 1, right? This is point 2, this is 1. So the image of this element is point 2 comma 1. Whereas suppose we use this decimal expansion of that number, f of point 2 is point 2 comma 0. So the same number under this map is mapped to two different elements in the square. So the map is not well defined. The way, at least the way we have defined it, it's not well defined. So in order to fix this issue, what we do is that we fix the decimal expansion uniquely. So we don't allow this multiple decimal expansion for the same number. And this happens only in the cases where you have repeated 9. So what we will do is that we will fix the convention that we are not going to consider the point 2 decimal expansion. We are going to consider only the repeated nines, infinitely repeated nines decimal expansion. So we will ignore this decimal expansion. So in that way, we don't have any well-definedness problem. We have unique fixed. Okay. So with that thing, we can actually see that the map that we have defined is actually a surjection, except that it's not defined for all elements x and y. Now the issue is that it is we defined f from 0 1 to the square. We made it well defined by fixing our decimal representation. Now what we are claiming is that not all elements in 0 1 are mapped by this map. Okay, so there are some elements which are not mapped to the square at all. So let me give you an example. Uh, for instance, take this number, okay, and which is a number in the closed interval 0 1. Okay, take this number, and f of this, that is f of this, there is no ab in the square such that f of this is this number. Okay, so this number is not mapped to the square at all. Let's see what is the map by definition. So by definition, where does this number get mapped? Okay, gets mapped. So look at, by definition, image is, what we do is that you see we have to take all the odd thing in the first quadrant, which is 1 3 4 5 6 7 8 9 0 1 and so on. So 1 3 4 5 6 7 8 9 0 1 2 3 and so on. Okay, so this is the first one, and then the even position, which is 2 0 0 0 0 0 0. So 0.2000. That is how this number is taken. Okay, so this is the image of this element, and this element, okay, now this element, by the way we have fixed here, that we will allow only infinite nines. Okay, by with that choice of decimal expansion, this element is actually the image of this element here. because if you look at this element, you see all the positions, all the odd positions is this, which is same as the first component here, and all the even positions is 0.19999, which is this, and this is what we are we are choosing, we are identifying this as point 2, right? That's what we decided to do. So this is the element that gets mapped to this number. So that is, and this element is not mapped to any point on the square because of the fact that we have chosen this decimal expansion. So this is another issue, that this f is not defined for all x in 0, 1. Okay, so how do you fix this problem? To fix this problem, what we do is that we assume one more assumption on this map, right? How this function f behaves. We are going to make one more assumption on f, is that the following: that to avoid situations like this which we have before, what we do is that whenever the decimal expansion, that is the number that we choose, the issue here was this, that it had alternate zeros, you see. So which is what made this 0.200000 so on, and which is what we don't consider, because we are going to consider this expansion. So the issue comes only when we take numbers whose decimal expansions have alternate zeros or zeros, right? Alternately zeros. So to avoid this kind of situation, the way we will tweak this map is that whenever we have a number with all its preceding zeros, right, which has zeros kind of interspersed in the thing. So what you do is that you consider that as one single unit. You don't see them as different numbers. For instance, whenever you have, like here, 0, so the same number here, whatever we have taken here is what we have taken here, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9, and so on. Okay, so whenever you have such a situation, what you do is that you think of 1 as a number which is in the first position, the second position is 2, the third position is 3, ideally the fourth position is 0, but now what we do, we will take 0 and the first non-zero number after 0, which is 4 here. Together this we treat as one unit and call this as the fourth position. So first position, second position, third position, 0, 4 is the fourth position. Similarly, now there is a 0 and next non-zero number is 5. 0, 5 is the fifth position. 0, 6 is the sixth position, and so on. Now you write that position. First position is 1, third position is 3, fifth position is 0, 5, seventh position is 0, 7, ninth position is 0, 9, okay, and so on. And then the 10th position is all this 4-digit number 0001. So this is the 10th position. The 11th position is 02, and that's why you have 02. Okay, so that is how we are going to. So we will treat this map whenever you had zeros alternating, then you treat every number up to the next non-zero as one single unit, with that as a position. So now with this, with that understanding, this map is going to give you this as a first component and this as a second component. Okay. So now this number gets mapped. So earlier this number was not mapped to any number on the square. Now this number is mapped to a number. We have given meaning to that as well. Okay. And this map, it's a surjection and also an injection. So this is a bijection. So what we have done is we have constructed a bijection from the closed unit interval to the closed unit square. So, and this is a proof of Cantor, and you can see the kind of proof it is. It's typical Cantor type proof, right? Okay. So now next question is, Can you have a continuous bijection? The same question that we asked before. So now we have a bijection from interval to square. Can you actually have a continuous bijection from interval to square? And the answer is no. This was proved by Netto in 1879 itself, right? They proved that there is no continuous bijection from the unit interval, closed unit interval to the closed square. And the proof is something which we have already used when I showed you the first example. So the proof depends on the fact that any continuous function, the continuous image of compact sets is compact, and the continuous image of connected set is a connected set. We need to use this. So if you don't know these proofs, please go and have a look. The another result that we will use is that if you have an injective map on, between two metric spaces such that the domain is compact and the function is continuous, then the inverse is also continuous. So this is again I kind of leave it for you to go and have a look for it. So go and look for the proof of this theorem. So here what is the saying, that if you have an injective map and the domain is compact, then for any continuous function the inverse is also continuous. The inverse, to talk about the inverse is why you have this injective assumption, right? So it's an injective map, so the inverse map will exist. So if X is compact and if F is continuous, the inverse is also continuous. This is not true if you don't have the assumption that the domain is compact. As an example, so this compactness of the domain X is essential in the above result. So as an example, you can see that if you take this map, this is not a compact set, right? It's open at the endpoint 1. So if you take this map fx, which is e power I2, so this maps the unit interval to the unit circle, right? It maps it to the unit circle in the complex plane. And you know that this map is 1, 2, and 1, 2. Okay. Now, but in this case, if you take the inverse map, it's not continuous at the point f0 equal to 1. So if you look at this, so the 0 is mapped here to 1, right? E power 0, which is 1. So 0, f of 0 is 1. If you look at this f inverse map, which is defined because f is injective here, it's actually bijective, right? So you have f inverse. This f inverse is not continuous at the point 1. Okay, why it's not continuous at the point 1? Because if you look at the sequence 1 minus 1 over n in this interval, which will converge to 1 here, right? Now the image of that on the circle, right, converges to f of 0. And this is because f is continuous. So f of 1 minus n converges to f of 0. F of 0 is 1. While if I take f inverse, which is 1 minus 1 over n, do not converge to do not converge in 1 because this converges to 1, which is not in this domain. So f inverse is not continuous in this domain. That is because you did not have compactness of this domain. Okay. Now we will show that there is no continuous bijection from the unit closed interval to the unit square in R2. Okay. So whenever there is a bijection from the interval to the square, then that map cannot be continuous. That's what this result is saying. So what is the proof? Suppose that map is continuous, then since f is a bijection and 0, 1 is a compact set, then by just the theorem that we just showed, so bijection, continuous map, so f inverse should also be continuous. So now you take the 2 points f of 0 and f of 1 in the square, right? 0 and 1 are here, so bijection is going to map 0 and 1 to some point to take those points f of 0 and f of 1 in the unit square. Now these are two distinct points because f is injected. Now what you do, you take two curves, gamma 1 and gamma 2, with disjoint curves in the unit square whose endpoints are f0 and f1, right? So these are 2 points on the square. You just take two curves joining f0 and f1. So uh, two disjoint distinct curves. Let's call it gamma 1 and gamma 2. Such a thing is possible, right, in R2. Now if you look at f inverse of gamma 1 and f inverse of gamma 2, because f inverse is a continuous function by that previous theorem, and gamma 1 is a path connecting f of 0 and f of 1, and gamma 2 is also a path connecting f of 0 and f of 1, continuous function. So it's a continuous image of a connected set, so it should be connected in 0, 1. Okay, and it should be connected in 0, 1, but the endpoints are actually f of 0 and f of 1, whose inverse, so f inverse of f of 0 is 0 and 1. So these are actually connected subsets of the interval 0, 1 containing both 0 and 1. Okay, which means that you have f inverse of gamma 1 and f inverse of gamma 2, both are mapped to the full interval 0, 1, which contradicts the injectivity of f, right? Because there now for every point here you have two different images, right? So the function f cannot be continuous here. Okay, so you cannot have a continuous bijection. So this is fine. This was also the case which we have seen earlier, right? We couldn't have a continuous bijection even from interval to open interval to closed interval and so on. So now the next natural question was, okay, we don't have a continuous bijection. Can we have a continuous surjection onto the square? So this was shown by piano, okay, and this is how the space filling curve. So when you think of the square as a two-dimensional object, when you say there is a continuous map from the from an interval, it basically means it's a curve, right? The image is a curve in R2, right? So when you say there is a surjective map to the square, which means that every point of the square is mapped, I mean is achieved is by this map, which means the curve touches every point of the square, which means all the points on the square is intersect is so is so um, sorry, so the curve passes through all the points on the square, right? That's what surjective means, right? Every point is taken by the curve. So this is why it's called the space filling curve. Okay, and though there is no bijection, Piano showed that there is a continuous surjection. That means you actually have a space filling curve. This is very useful in modern times also in many things, like even to pack things in all your electronic items and many things. Uh, it's a very optimal way of arranging or making kind of network connections or electronic board, that motherboard that you see, all these connections. So to kind of utilize the maximum thing, even there are even antennas which use this idea and so on to receive signal of all frequencies or to maximize the frequency receptor and so on. Okay? And and especially when you have smaller devices like mobile phones and so on, you need to have a very small antenna, and that small antenna should be able to receive most of the frequencies and so on. So space filling curve. Uh, is so this existence of this continuous surjection was proved by Piano in 1890. So we are going to give one such curve here. So we are going to construct a curve in R2 which passes through all the points of the square. Okay, and that needs two results. First one is the Weierstrass M test. Weierstrass M test tells you that if you this is like the comparison test, but right, where even this also where depending on the n, right? So if you have a sequence of functions such that each of them is bounded by some number, but it's not uniformly bounded, but they're bounded by some number, but such that all these bound that as a series converges, then the series for Fn also converges uniformly in the domain that you are taking. So this is Weierstrass-Young test. Okay? The next result that we will want is, so if f is the uniform limit of this series Fn, okay, in its domain, if Fn is continuous at x naught, then the uniform limit series, so uniform series, the uniform limit of the series is which is summation Fn, that is also continuous at x naught. Okay, that's what this theorem is. Okay, this again we are not proving. You please fill this gap, try to find a proof. If you don't know, if you're not aware of it, at least learn the proof. Okay, these things are available in most of the analysis books. Okay, so we would use these two results to actually construct our continuous surjection onto square, which means we will going to construct the space filling curve. So how do we do this? So we take, let's take this map f from 0, 2 to 0, 1. Okay, so the domain is 0, 2. Later we are going to whatever factor it out and so on, that you will see. So you take this map 0, 2 to 0, 2. What we are doing here in this map is that we are dividing 0, 2 into 6 parts. Okay, so each part is of length 1 over 3. Okay, so in the first part and the last part of the division, we put the function to be 0. So if you think of the graph of the function, the first one, so in the first 1/6 part of this interval, it's 0, and the last 1/6 part of the interval, it's 0. Okay, and then the second 1/6 part, sorry, here this is the 1/3 part, right? You will have you are making 6 parts of this, and each part is of length 1 over 3. Okay, so the second 1/6 part is given by this straight line, which is of slope 3, passing through uh, with an intercept of -1. Okay, so this basically at t equal to 1 over 3, this is 0, so it matches with this. So it's actually continuous. Okay, so kind of piecewise continuous function. So from 1 over 3 to 2 over 3, it's 3t minus 1. Then from 2 over 3 to 4 over 3. Okay, there are two parts here. That is, entire thing is a constant function 1. So if it's 0, then it increases from 0 as a straight line with slope 3, and then it becomes the constant function 1 up to 4 by 3, and after 4 by 3 it falls down with slope again -3 slope, negative slope, it falls down, okay, at 5 by 3, and after 5 by 3 it's 0. So that's this map. Now this map, the way we have defined, we can extend it periodically with period 2. So we have defined in the interval 0, 2, you see it's piecewise continuous function, and it's 0 at the end point. So it has as a 2 periodic function, you can extend it to the entire real line. This function can be extended to the entire real line. So the new f that we have obtained is a map from R to 0, 1. Okay, the entire real line is the domain now, which is a 2 periodic function from what we have constructed. Then what you do, you define two because we need to map it to the square, right? So we are going to define two functions f1 and f2 on R using this little f, such that f1 of t is the limit of this series, f2 of t is the limit of this series, okay, which is nothing but f of this value over 2 over n, f of this value over 2 over n. Okay, so now we have f1 and f2. Now by the Weierstrass M test, which we just stated in the previous slide, if we choose Mn to be 2 power n, then this both these uh, both these series will converge uniformly by Weierstrass M test because they satisfy the hypothesis of the Weierstrass M test. Okay, so they converge uniformly, so there is no issue of convergence here. So the choice of Mn that you need to make is 2 power n. Okay. Okay. So just to so this is the one that we are talking about, right? Each f mod fn should be less than or equal to mn, and we are just saying that. So here the fn is whatever we have here, okay, and this is less than or equal to 1 over n because each of the f was less than 1 here, you see, the way we have defined here. Okay, so now since f is continuous on R, that's how we did it because it was a piecewise continuous function, right? It's a continuous function. But yeah, it's a continuous function the way we have defined. So f is a continuous function on R. So f1 and f2 are also continuous. This is the second theorem that we had talked about right here. That if you have a uniform limit of a series, if each of them is continuous at a point, then the limit is also continuous at a point, right? So here each is this, so this f is continuous, so each of the term here is continuous, so the limit is f1, which is continuous. Similarly f2 is also continuous at every point because it's continuous at every point. Okay, so recall that this series 1 over 2 power n, that is a geometric series, right? This converges to 1. So from that we can conclude that these limits are actually lying between 0 and 1 and 0 and 1, which means that f1 comma f2 actually goes and falls in onto the square, right? If I define a map like that, so if I define a map such that this is the first component, this is the second component, then f1 comma f2 lies on the square. That's what we have verified here from the fact that this limit is 1. So both of these have value between 0 and 1. So f1 comma f2 will lie in square. So that's what motivates us to define this capital F, which is f1 comma f2. Okay, and that fills, and we will show that the image of this function is the map that we want, which is the continuous surjection, the space filling curve that we want. So for proving surjection, what we need to show is that if we take any point in the square, we should be able to find an element in 0 1, in C in 0 1, such that f of C is a comma b. That means we need to show that if I take any C, then f of C by definition is f1 of C and f2 of C. So we need to show that f1 of C is A and f2 of C is B. Okay, that's what we need to show. So we need to, given AB, we need to find the C. So suppose A and B are given, both are A is from 0 1, B is also from 0 1s, right? So so we write down the binary expansion of both the numbers A and B. So this is the binary expansion of A, this is the binary expansion of B. The way we wrote down decimal expansion before for some earlier proof, here we are looking at the binary expansion. Which means that all these an and bn will have values either 0 or 1, right? Because it's a binary expansion. So now you define C. So we are going to define C. So given AB, we need to obtain a C, right? So we got so we took a AB, we wrote down their binary expansion, and now we are defining C to be 2 times summation of Cn over 3 power n. Okay. And the way Cn are defined is that whenever the index, whenever this subscript is odd, we give an value. So C2n minus 1 is an value and C2n is bn value. Okay, so this is how we define C, and we need to show that f1 of C is A and f2 of C is B. If we show that, we are done. Okay. So once we have the C, we immediately see from this fact, from this geometric series fact, that this limit of this 2 times of this series is 1. Okay, so from this we actually see that the value of C is also between 0 and 1, the same argument that we used here, right? So the value of C is between 0 and 1 because Cn is anyway either 0 or 1. So, and this series, so this is less than or equal to 1 times of this, and that series is 1. So the value of C is between 0 and 1. Now you fix a non-negative integer, right? You fix a non-negative integer k and look at what is 3k plus c, right? The reason why you are looking at 3k plus c is that this is what we want, right? We, by our definition of f1 involves f of 3 power something of t, and f2 of t involves f of 3 power 2 and 3 power something else of t. So we want to show that f1 of wherever we put t equal to c, we want to show f1 of c is a, f2 of c is b. So we should ideally know f of 3 2n minus 2 of c. Similarly, 2n minus 1 of c, and this we should know for all n, right? That's what we are trying to see there. So that's why we looked at 3k power c. If I look at 3k power c, then you split the by the definition of c, right? C is this. So I multiply 3 power k here, I multiply 3 power k here. So I bring the 3 power k inside, and this has a sum 1 to infinity. So you split this sum up to k and then after k. That's what it is. So once you fix a k, this k is fixed. So we were looking at 3k plus 3k power c. 3k power c is precisely that sum split into two terms, where one is up to some k, another is k plus 1 to infinity. So you call this first term as, suppose you call this as uk, and call this second term as vk. Then 3k plus c is uk plus vk. Okay, where vk is precisely this term, which, and here I have rewritten by changing this index to 1 to infinity. That's it. So vk is this. Okay, so now what you observe here is that look at uk. uk by definition is this 2 power 2 times something. 3n minus k comes on the top, k minus 1, because in this sum, once you fix k, n is always less than k. So k minus 1 is positive. So this is a positive quantity, this is 2, right? So this is some number either 0 or 1, right? That's what we have seen already. So this is actually some number multiplied by 2, right? This is an integer, 3 power some positive thing. So this is some integer. So 2 times that integer will be an even number. So UK is always an even integer. So UK is always an even integer. Recall that we said F is a periodic function of period 2, right? So when UK is an even integer, it is multiple of 2, right? So 3k plus c, if I look at what is f of 3k plus c, f of 3k plus c is f of uk plus vk. But uk, as we have seen, is a even integer. So f of uk plus vk by the periodicity of f is f of vk. So that is why f of 3kc is f of vk. Okay. So now we verify what happens to vk from our definition. So this is our vk here. Okay. And we are going to relate vk and the first coefficient here. When m equal to 1, we get ck plus 1, right? So first coefficient, we are going to relate it like that. We are going to see a relation. So recall that the ck's were chosen, the c and here were chosen as a and bn, and a and bn were the binary expansion, so it is 0 or 1. So ck plus 1 is also either 0 or 1. So in this vk term here, if I put m equal to the first term here has this coefficient ck plus 1, right? So ck plus 1 is either 0 or 1, right? So let's see what happens in the case when ck plus 1 is 0. So if ck plus 1 is 0, then vk is lying between 0 and 1 by 3. Why? Because ck and so plus 1 is 0, and every ck plus n is either 0 or 1. The lowest value is 0. So if I put 0, I get 0 here. The highest value possible is 1, so that you have the series which is converging to 1 by 3. So that way we have shown that f of vk is actually 0 because that is by the definition of f. F was 0 whenever any number was lying between 0 and 1 by 3. So vk is now lying between 0 and 1 by 3 whenever ck plus 1 is 0. So f of vk is 0, which is same as the value ck plus 1. So whenever ck plus 1 is 0, the f of vk is ck plus 1. And what happens when ck plus 1 is 1? When ck plus 1 is 1, the same argument, you have the series. Look at the first term, that is 2 by 3, then the rest of the terms with 0, and the rest of the terms with 1. This is equal to 1. So in this case, vk lies between 2 by 3 and 2 by 3 and 1. And we have already seen that the value of f between 2 by 3 and 1 is 1. Right? You remember that? You see, 2 by 3 and 1. 3 by 3 is lying in between here, is the value is 1. So yeah, so what we have is f of vk is 1 here, which is the value ck plus 1. So f of vk ck. So in both the cases, whether it's 0 or 1, what we have obtained is that the value of f of vk is ck plus 1. Irrespective whether it's 0 or 1, whatever it is, f of vk is ck plus 1 is something that we have obtained. And f of vk is what we have here. F of vk is ck plus 1. So f of 3kc is f of vk, which is ck plus 1. So f of 3kc is equal to ck plus 1, and this is true for every choice of k, right? We already fixed k in the beginning when we started here. We fixed k here. So for all k0, for all non-negative integer k, f of 3k plus c is ck plus 1. Now let's go back to the definition of f1 and f2. Now we can put k equal to 2n minus 2, we get the value. We put k equal to 2n minus 1, we get this value, right? That's what we are doing now. So you put k equal to 2n minus 2n minus 2. This is by this formula is c2n minus 2 plus 1, which is c2n minus 1, which is precisely an. Similarly, f of 3 2n minus 1c is c2n, which is precisely bn. Okay, so if you replace in the definition there with a and bn, where is the definition? Yeah. So this becomes an, this becomes bn, and that is nothing but the binary expansion of a, this is binary expansion of b. That is how we have shown that the f of 1 of c is a, f of 2 of c is b. Okay, and that way we have shown that for any choice of a, b, there is a c in the interval such that a, b is an image of that c. That way we have shown that this map is, the map that we have defined from 0, 1 is actually a, this is actually a surjective map. Okay, so with this we have completed the space filling curve. We actually explicitly constructed one space filling curve. There are other things you can go and have a look. There are this piano's curve and the Hilbert's curve. All these are space filling curves. Okay, so you can go and see it in your kind of leisure time and so on. Okay, then see you in the next lecture. Thanks a lot.